Welcome to the week 12 of our calculus course. Today we will review sigma notation and its properties. Sigma notation we're going to use in class this week to learn how to define definite integrals, how to calculate area between the curve and x-axis using Riemann sum. When we're looking at the sum of n terms, let's call them a1, a2, a3, and so on, an. The short way of writing this summation is using the sigma notation. Sigma is a Greek letter and it makes sound S. We'll use it to denote summation. Little I is an index. It has the lowest value indicated on the bottom below letter sigma, and the highest value of the index I is indicated above a letter sigma. I, since it's index, it basically indicates which term of the sum we're looking at, first, second, third, or n's. AI is the expression of the i's term of the sum. Let's look at a couple of examples. Say we have a sum where index is changing from 1 to 4 of the expression I squared. The lowest value of index is 1, therefore 1 squared is the first term in the summation. Then the index will take on all positive integer values up until 4. So then, if I is equal to 2, 2 squared is going to be our second term in the sum, while 3 squared is the third term in the sum, and the last, fourth term in the sum would be 4 squared. Let's consider the sum of 5 as I changes from 1 to 3. The lowest value of index is 1, so then if I is equal to 1, the expression that we try and sum up is 5. When I is equal to 2, the expression is still 5, and when I is equal to 3, the expression is exactly the same, it's 5. So we have 3 5s added together. Now let's consider the sum where index doesn't start from 1. Say here is a sum as index starts from 2 to 5 of the expression 2i. When I is equal to the lowest value 2, 2 times 2 is 4, and that's our first term. The second term is when I is 3, 2 times 3 is our second term. I raises up to 4, giving us 2 times 4 as a third term. And the last term in the sum is when I is equal to 5, 2 times 5 is the final term in the sum. There are 4 very useful properties of the summation. Let's review them. Let's say we have a sum as index changes from 1 to n of a constant c. It means that the constant added to itself n times. So not surprisingly, the sum is equal to c times n. Let's consider an example where n is equal to 3 and c is equal to 5. So sum as index changes from 1 to 3 of 5s, which is 5 plus 5 plus 5, would be equal to 5 times 3, it is 15. Another property is when we sum it up, constant multiplied by the expression ai as I is changing from 1 to n. Since every single term in the sum has the common factor c, we can factor it outside of the sum. So it's equal to constant c times the sum of ai terms as I is changing from 1 to n. In our early example, we have had sum starting from 2 to 5 of 2i. This is 2 times 2 plus 2 times 3 plus 2 times 4 plus 2 times 5. We clearly can factor out 2 and have 2 multiplied by the sum 2 plus 3 plus 4 plus 5, which can be written as 2 times the sum of i's where I is changing from 2 to 5. Clearly 2 plus 3 plus 4 plus 5 is 14, so 2 times 14 is 28. The last 2 very useful properties are sum over sum, or sum over difference. If we have every term as sum ai plus bi terms, we can calculate sum of terms ai separately, sum of terms bi separately, and then add the results. Similarly, if we sum up difference ai minus bi, we can sum up ai's terms separately, sum up all bi terms separately, and then subtract from sum of ai's the sum of bi's. Let's look at how to use the properties sum of a difference to calculate sum of I minus I squared if I is changing from 1 to 4. If I is equal to 1, 1 minus 1 squared is our first term of the sum. For I equals 2, we'll have the term 2 minus 2 squared. When I is equal to 3, it's 3 minus 3 squared. I equals 4 produces 4 minus 4 squared. If we group together all the terms that have no squares, we will get 1 plus 2 plus 3 plus 4. Now, all the terms that have squared are minus 1 squared, minus 2 squared, minus 3 squared, and minus 4 squared. So if we factor out minus 1, we'll have a sum of squares of 1, 2, 3, and 4. We can write this as sum of i's as I changes from 1 to 4 minus sum of I squares where I is changing from 1 to 4. When the index n is a large number, sum of i's or sum of I squares will be calculated using one of the following useful formulas. Sum of i's as I changing from 1 to n can be calculated as n plus 1 times n divided by 2. Sum of I squares, where I is changing from 1 to n, is calculated by the formula n times n plus 1 times 2n plus 1 divided by 6. In our case, the largest value of the index I equals to 4, so n is equal to 4, and we'll get that the sum of I minus I squared as I changes from 1 to 4 is equal to negative 20. It's worth noting that there are common errors related to the properties of sums. Often, the assumption is made that the sum of the AI times BI can be written as the sum of AI multiplied by sum of BI. This is not correct. Let's take a look at the simple case where index n is equal to 2. So, we'll have two terms. I is equal to 1 produces A1 times B1, and I equals 2 produces A2 multiplied by B2. Left-hand side, sum of AI BI, as I changes from 1 to 2, is equal to the sum of two terms. However, sum of AI will have two terms of our own, A1 plus A2, where sum of BI's, as I changes from 1 to 2, has also two terms, B1 plus B2. If we open parentheses in our right-hand side, we will notice that on the right side there are not two but four terms, A1B1, A1B2, A2B1, and A2B2. So of course, the left-hand side and the right-hand side are not the same. Therefore, we know that the sum of the product can never be written as the product of the sum. Similar error comes in from making an assumption that sum of the quotient can be written as the quotient of the sums. Let's take a look at the example. What if we consider sum where index I changes from 1 to 2 of a quotient I divided by 3? I want to show you that it's not the same as the sum of i's, where I is changing from 1 to 2, divided by sum of 3's, where I is changing from 1 to 2. When I is equal to 1, I divided by 3 on the left side is equal to 1 divided by 3. I is equal to 2 produces 2 divided by 3. On the right side, however, in the numerator, sum of i's as I changes from 1 to 2 is sum of 1 and 2. In denominator, we have sum of 3's as I changes from 1 to 2, so it's 3 plus 3. Clearly, on the left-hand side, 1/3 plus 2/3 equals 3/3, or 1. On the right side, we get 1 plus 2, which is 3, divided by 3 plus 3, which is 6. 3 divided by 6 is a half. 1 is not the same as a half. So, there is no property that will allow us to break sum of a quotient as a quotient of the sums. I hope that you have found this review of summation notation, properties, and the common errors associated with the sums useful. Until next time.